For our BJT bias circuit shown, we're asked what is the base current IB in milliamps. We're going to use the following variables. We can assume that the transistor is in the forward active region, and using the forward active region, we can do a control or command F and search the notes linked below the like button in the description for the actual equations for this. The equation that we're going to first start out with is that our IB, which is what we want to find, it's going to be this value right here, is equal to a IC over beta. Now, we don't know what our IC is, so let's continue to write this out more. This is like part one. Part two, our IC is going to be equal to alpha times our IE. Now we want to rewrite our alpha because we don't have alpha, but we can rewrite this and set this equal to a IE times beta, and this is all divided by our beta plus 1. And so all we need to find is our IE now, and we're given our IE right here. We're not given it, but we can solve for this right here. We can easily solve for IE, easier than solving for our IC. And so we can just plug this in back here. So rewriting this out, our IB is going to be equal to, we have our IE over the beta plus 1. So now we need to solve for our IE. And the way we would do this is by rewriting this so we can see it a little bit easier. If we have, and we'll do this over here, our voltage as VCC, like this, and it's going across some resistor, RE, we know we have our voltage E right here, and then we have the BJT right here, and then it's going to go to our VC, we're going to have our resistor, RC, and so far this looks very simple, very familiar, but this is where it changes a little bit. So we still have our IC going through here, we're going to have our IB across here, and our IE across here. The difference is that we're not going to have the top left part. So instead, we're going to have a resistance of RBB, and then we are going to have a VBB, or this is going to be a VB for a base emitter, and then we have a VBB right here. And this is going to go down like this. And our RBB is equal to our RB1, which is in parallel with our RB2. So now we can easily solve for this. We're going to be looking at all of the voltages through here. So we're going to do like the node voltage method. We have our VCC going in here. And so all the voltages that are here and here are going to be equal to our VCC. And since they're equal to our VCC, that means that our VCC is equal to, first, we of course have our IE times our RE. So that's going to be the first thing that we have to look at. We're going to add to this. We have our VBE, the base emitter, right here. So we have VBE. We're just adding up all the voltages here. What's the next voltage? Well, we also have a VBB. So we do plus VBB. Plus, lastly, the voltage across here. So that is going to be our VC, or we can write this as our not our VC, but we don't care about this VC because we have the battery right here. It's gonna take care of that, so it's gonna go through this way. So we're gonna have our IB times our RB, and that's going to be right here. Now this is RBB. So what we can do is start rearranging this so that we want to solve for our IE. We can rewrite this IB as IE over beta plus 1, just from what we've learned up here. We can rewrite this. Now we can rearrange it. So if we move all of the other variables onto the other side, so we'll have our VCC minus our absolute value of our VBE minus our, and then we have our VBB as well. And this is going to be set equal to, well, we have our IE, we can factor it out from each of these. So that's going to leave us with an RE plus an RBB, and this is all over our B plus 1, or beta plus 1. And now we can multiply this to the other side. So we're going to have a VCC minus the absolute value of our VBE minus our VBB, and this is all happening over our RE plus the RBB over the beta plus 1, and this is equal to our IE. So that's the equation that we're going to plug into here. Now we can write this part out. IE is equal to, our VCC is 15. So if we write this, we're going to have a 15 minus our VBE, which is 0.7 volts, minus our Vbb. And the Vbb, we need to solve for this. We actually don't know what this is right now. So solving for our Vbb, what we're going to have is a voltage division, because this right here, it's happening across this resistor with this voltage coming in. So if we were to rewrite this, we have like our VCC, we have our RB1, and then we have our RB2, and this is going to be our like VBB, and it's all connected to one ground. So we have VBB is equal to, we have our source, which is 15, we have the voltage that our VBB is over, so that's going to be the RB2. So we have 15 RB2, and this is all happening over RB2 plus our RB1. And this is, again, our VCC. So now we can plug the values in right here. So we have minus inside of here. We can combine the VCC, so we're going to have 15 times our RB2, which is 33.8. Make sure you include the units, or you can cross them out because we have a 33.8 on the top. And then on the bottom, we are going to have our 37.1 plus the 33.8. So they would cross out. Now we go to the bottom. In the bottom, we have our RE. It's given to us as 4.7 times 10 cubed for the kilo. Then we have a plus our RBB, and then our beta plus 1. Resistors in parallel now, we have 1 over our 37.1 times our 10 to the cubed. This is important because on the top we're going to have like a 10 to the 6, and then on the bottom we'll have a 10 to the cube. So when we combine them, it'll really just be like 10 to the cube. This is going to be a 1 over our 33.8 times 10 cubed, and this is raised to the negative first power. And this is all going to happen over our beta plus 1. Our beta is going to be, and we can just close this out, we've given a 44, so we have 44 plus 1. And so we can take all of this and plug this right into here. If we do that, we're going to have the following equation. 15 minus 0.7, right here. We have our 15 times the 33.8, 37.1, 33.8, 4.7 times 10 kilos on the bottom, and then we have the resistors in parallel. We have our 44.1, and then the bottom part, this 44.1 over here, is because we're plugging it back into our IB, so we have beta plus 1, and then we have it being multiplied by 10 to the 6 because we want our answer in microamps. And so that means our answer is going to be approximately 31.19328. Now your answer might be a little bit different, but the process is the same, and we have other videos on how to find like the resistance, and that is a very similar process as well. But that's it for this problem and how we would go about solving for it.